Okay, thank you very much. It's always a pleasure to visit here. I seem to come here about twice a year, so... and like I say, it's just to bring everybody up to date about where we are with the ELT, since it's, I haven't given a talk here for a while. And there is now significant movement of what's going on in the ELT, in particular the instrumentation program. So what I'll talk about is what are the challenges and problems of mounting big instruments on big telescopes. Then I'll go through the ELT first light instrumentation program, where we are. So that's HARMONI, METIS, and MAORY MICADO. And then I've got a couple of last slides that's actually slightly different, just on what the current status is of the ELT. So just to tell you exactly where we now are with the ELT and what's going on. So the first question is, okay, why do we go to bigger and bigger telescopes? And fundamentally it's because astronomers always want to observe something that's just a little bit too faint for their current telescopes. So they end up spending an awful lot of time observing things that they can just get to with a very poor signal to noise. Well, that's what it seems to be. And so the bigger the telescope, in theory, the fainter you can get. And so the time to reach a specific limiting magnitude goes as either 1 over d squared, if you're seeing limited, or it goes as 1 over d to the 4th, if you are background and diffraction limited observations. So when you're using AO, and you're getting really diffraction limited observation, then the time to do an observation goes as 1 over d to the 4. Now, the ELT is a factor 5 bigger than the VLT. It's a factor 4 bigger than GTC, approximately. And so what that means is, in this diffraction limited and background limited case, that the ELT will do the same observation 500 times faster than would do the same observation on the VLT. That's to reach a specific limiting magnitude. So that means that in the diffraction limited mode, 1 hour on the ELT would take you 50 nights on the VLT to get down to the same limiting magnitude. And so that's basically, this takes you therefore into totally new science areas that we can't currently do. But the basic challenge is that the diffraction limit, when you look at the spot produced on a detector or the spot produced on the focal plane, is basically independent of telescope size. It's 40 microns. So for an f/70, it's basically dependent on f ratio. So most big telescopes are f/15 to f/17. And so you work out what it is in the K-band, and that comes up with 40 microns. And so what this means is you have to hold a spot in the focal plane accurate to 40 microns, irrespective of your telescope size. And so it's true for the VLT, which weighs hundreds of tons and has a focal length of 120 meters, or the ELT, which weighs thousands of tons, and you have a 700-meter focal length. So you've got your mirrors 700 meters away in effect, and you still have to hold that point to 40 microns. And that is a huge problem. And so all the problems that we have, therefore scale with either, or you find a scale with either d or d squared. And this is really where the ELT is really pushing us, because usually changes in telescope sizes have been a factor 2. If you look back through history, the biggest change that we've had at any one time is basically a factor 2. That's when they went from the Mount Wilson to the Mount Palomar telescope, which was a 2.5 meter to a 5 meter telescope. But now we're going up by a factor 5. And so the problem is that d, or if you get problems that are changing with d squared, these are now a factor 20, 25 times harder than anything we've dealt with before. Now, to get to the diffraction limit, obviously we need to use adaptive optics. And this is driven by R0, which is the size of the atmosphere, which is basically the cell size in the atmosphere, which you can say is 50 centimeters or so. And so what in an AO system you basically have to do is to break up the pupil of your telescope into subsections that are 50 centimeters across. And so for the NTT, which is a 3.5 meter telescope, this is basically 7 by 7. So you need 49 subapertures and you'll get diffraction limited. On the VLT, it's 16 by 16. GTC, it will be about 20 by 20 subapertures. So again, you're talking about a few hundred subapertures. On the ELT, we need 78 by 78. And so in order to get diffraction limited, we need something like 4,200 subapertures. But we still have to read them all out in the same time, because it's all driven by the atmosphere moving through the telescope. So we still have to read them out in basically 2 milliseconds and make the correction. And so basically, the number of apertures in the wavefront sensor goes as d squared, and the number of actuators in the deformable mirror goes as d squared. So instead of having an array of a few hundred that we're running 500 times a second, we now have a few thousand that we have to run 500 times a second. Now, what is unique on the ELT, as I'll mention a bit later, is that in the ELT, we actually have a deformable mirror as part of the telescope. So M4, the fourth mirror, is a flat 2.5 meter deformable mirror with about 5,000 actuators behind it. And this is used by all instruments. So it's not like, for example, GTCAO, which is a self-contained system that sits behind the focal plane. No, in this case, the ELT is part of the adaptive optics system. Now, another problem is SCAO is fine, but it will only cover 0.1, 0.2% of the sky. And particularly if you want to do extragalactic science, there's simply not enough guide stars up there to use, so we have to start using lasers. And lasers are a real problem as you go to bigger telescopes, because again, it scales rather badly with the telescope size. So one of the problems is the laser itself is produced, or the laser guide star is produced at a height of about 90 kilometers. So it's not at infinity. All the objects you're looking at are at infinity. And so the distance, and so the laser guide star is produced in focus significantly behind the focal plane. Now, on the VLT, this is something like 6 to 18 centimeters, and we have AOF running on UT4. And so, okay, it's a few centimeters behind the focal plane, but you get this guide star, and it's not that difficult to include within the system. On the ELT, because of this very, very long focal length, it turns out that the laser guide star changes between 2 meters when we're at an angle of 60 degrees to nearly 7 meters when we're in the zenith. And so that's how far the in-focus guide star is produced behind the normal focal plane. And so this means the beam, as it goes through the focal plane, on the VLT, the laser beam, as it comes through the telescope focal plane, on the VLT is only about a centimeter and a bit across. On the ELT, it's 35 centimeters. So this is basically scaling as d squared. And so I'm very happy we're not building the 100-meter telescope. Otherwise, the out-of-focus image, as it comes through the natural guide star focal plane where you have to put your science instruments, would be 1.5 meters across. So it gets huge. And this is actually one of the limitations if we want to use lasers. This is basically the biggest telescope that you can realistically use lasers on, at least with our current technology, simply because of the problem of these two problems. This gets a lot bigger, and this gets a lot bigger, and then you realize you physically can't build the optics that size. The biggest refracting optics has hardly changed in 100 years. It's basically 1 meter. And so the optics now becomes a lot of a challenge. And then the final problem that we get is spot elongation. Now, spot elongation occurs because you launch a laser off the size of the telescope. In the lower atmosphere, you get Rayleigh scattering. And then the actual laser guide star itself forms a tube that's about 15 kilometers thick at between about 80 and 100 kilometers. And so if you're looking from this side of the pupil, you're basically looking right along the tube, so you get a point source. If we're looking at this side of the pupil, though, we're now hitting this tube at an angle, so it becomes significantly elongated. So this is some pictures I took off the web from Canary, who are doing tests on the Herschel of exactly this problem. And so they set up the laser so it would basically be the equivalent of the far side of the pupil on the ELT. So it's basically 40 meters away from where the telescope was. And then they look through Canary, how does the source elongate? And then this is a natural guide star. So natural guide star, you get kind of normal 1 arcsecond. But this is what the lasers look like. So you get these long, long lines. And we basically still have to work out what the atmosphere is doing, but now off a 20-second line from one side of the pupil, but on the other side of the pupil, you'll still be in focus. So we have this very, very large change in what the laser guide stars look like. And this is something that we're putting an awful lot of work into really understand what's going on and how to deal with it, because this causes an awful lot of problems for reconstructing the wavefront. So why else do instruments get big? Well, one of the problems is that most of the astronomical objects are kind of a fixed size. If you take Jupiter, On the NTT, physically as it gets to the focal plane, it would be 7 millimeters. That's the physical size of the image. On the VLT, it would be 23 millimeters. On the ELT, though, it's 13 centimeters across. So that's physically how big it is. That means if you want to take an image of Jupiter, you've got to take this 13 centimeter image, or part of the focal plane, and re-image it onto the detector. And so that pushes up the size of your instruments quite significantly. But there's another problem, or there's another effect. 1 arc second on the sky, okay, on the ELT this is 3.3 millimeters, but at the diffraction limit this is actually 80 resolution limits, or 80 resolution elements. So when we take our image we get 80 spatial resolution limits across 1 arc second. Whereas on the NTT, the plate scale is a lot better or smaller, and so you only get 7 resolution elements. So this means that if you want to cover 1 arc second on the NTT, you would only need about 15 pixels. On the ELT, 1 arc second, you would need something like 160 to 200 pixels. So you now need an awful lot more pixels on your detector just to cover the focal plane. So, because you need more pixels, you need to go for far, far bigger detector systems. Now, it is noticeable that we're building an instrument for the VLT, which is actually very similar to Frida. Frida and Eris are very similar instruments. They have a field of view of about 40 arc seconds, diffraction limited, or nearly diffraction limited. And they can do it on a 2K detector. MICADO, which also gives a field of view of about 50 arc seconds, diffraction limited, needs 9 4K detectors. So you're going from 4 million pixels to nearly 150 million pixels just to cover the same areas of sky at the diffraction limit. And it's the same with HARMONI. HARMONI is an IFU. Again, on Symphony, on the VLT, you can get away with, about 2,000 spaxels, spatial pixels. On HARMONI, we need 32,000 just to cover the same area of sky. And so for this is another reason why the instruments start to get huge. But there is another case. We will still have to do some seeing limited observations because we can't guarantee that we'll have perfect weather conditions in all cases. And here we start to run into basically it's an optics problem. The fastest cameras that you can realistically build are between f1 and f2. f2 is kind of the limit if you want a large area. So for example, EMIR on the GTC has an f2 camera, and that was built, it works well, but it was kind of pushing the limits. And so that on the GTC will give you 2 arc seconds per pixel. Now the same camera, which is nearly the limit of what you can build for the optics, will only give you 50 mass, so 0.05 arc seconds per pixel. And so in the seeing limited case, that means, so you say have 1 arc second seeing. On the GTC, you'll do it in 5 pixels. On the ELT, we now need 20 pixels to cover that. And so actually it's one of the things. If you want to cover area, then the ELT is not a good way of doing it. Because although it may be 20 times faster, you cover 1/20th of the area in the seeing limited regime. And so it means that whereas on the smaller telescope, or GTC being a smaller telescope, you could do if you can do the image in one go, on the ELT with the same system, you would need to do something like 16 images. And although the ELT will go 16 times fainter for each one, it's got to do 16 images just to cover the same time. So it turns out that in this case, you'd be étendue limited, and you'd be basically nearly as fast on the GTC as you would be on the ELT to actually cover the field. Also with spectroscopy, again, if you have a 1 arc second slit, this is for seeing limited. With the GTC, you can get 5 pixels across there quite easily, and you end up with 4,000 resolution elements. On the ELT, because you've got 20 pixels across the same size, you only get 100 resolution elements for the same detector. So therefore, you have to go to a bigger detector if you want to cover the same number of resolution elements. But for the same size pupil, the GTC will have 4 times more spectral resolution on the same prism, or on the same grating. So again, to get to the same spectral resolution, you would need to go to a grating that's now 4 times bigger. So instead of being 10 centimeters, which are interesting to do, but we can do them, we're now looking at 40 centimeter gratings. And these are getting big. And so again, it becomes an interesting problem. So the point is, the ELT is very good for certain ranges of science, but there's other science that you're better off on a smaller telescope. So you have to be careful. Now on the ELT, we actually have some added complications that we don't normally have on other telescopes. One of them is the ELT only has 2 foci. It's the 2 Nasmyth foci, and that's the only place we can mount instruments. And on one of them, or one focus, we have to mount the prefocal station, which has mirrors to split the beams off to various instruments, and the A and G system. And we want to mount 3 instruments and an AA system on the single platform, so they're all available at the same time. Another problem is the optical axis coming from the telescope is 6 meters above the Nasmyth platform. This was chosen so that some of the instruments can go to a gravity invariant mode by basically having a 45-degree mirror above them, so they need the space below the focus. But it means that the instruments are now, the beam is coming in at a very high height in comparison with GTC, where it's kind of 2 meters above the Nasmyth platform. And then the final problem we have is that the telescope is being developed at the same time as the instruments. And so because the telescope is new, the instrument is new, there's a lot of things that, if you go to a telescope that's already working, are well defined. And then the final problem is, of course, the scientific capabilities of each instrument. Each instrument, or everybody wants to build extremely challenging instruments that does extremely challenging science. And that leads to its own complications. So the telescope, the ELT telescope, is also slightly different. So this is, like I say, an artist's impression of the ELT, and this is the optical system. So rather than being a retrocation, which has 2 mirrors plus a Nasmyth, plus a flat Nasmyth to bring the beam out, here we have 5 mirrors. So it's a 3-mirror and a stigmat, which is the primary mirror here, which is a segmented mirror, the secondary mirror, which is a negative mirror, and then the tertiary mirror, which is actually a spheroid, has power. And this, so what happens is this produces an image of the focal plane about here. This is then re-imaged off this mirror into the focal plane. And then we have M4, which is an adaptive mirror that's available, therefore, to all the instruments, and M5, which is for tip-tilt correction. And it is because basically the range of tip-tilt correction that we need is far too large to take out completely on M4. And therefore, we need a separate mirror to handle this tip-tilt. So we can do tip. So we actually run them together. So the very fast stuff, up to 5, I mean, M4 runs at about up to a kilohertz. So we can take 1,000 references, or we can do 5,000 movements per second. So the high-speed tip-tilt, but only up to about 0.25 of an arc second, about a quarter of an arc second, is taken out on M4. M5 runs at about 10 hertz, but we can cover up to about 3 arc seconds. So it has a far larger range. So it's basically a woofer and tweeter in an audio system. Same idea here. And then this is what M1 looks like. This was a life-size model that they laid out on the lawn of what M1 actually looks like. So you can see some people there, so you get an idea of how big this telescope actually is. I mean, we could put the whole of the VLT mirror in the central hole to give you some idea of how big these things are. So it was recognized early that normal instruments, or shall we say the instruments, a simple extrapolation from the VLT instruments, was simply not going to work here. And so we actually started looking at the instruments in about 2004. And in 2008, we launched a series of phase A studies so that we had teams who got together and made proposals about the sorts of instruments they would build. This included high-resolution spectrometers, a multi-IFU system. So we could get an idea of what the instruments need from the telescope, and also how much some of these instruments were going to cost. There was then a series of decisions, which is on the next slide, and we actually then signed the agreements for the first light instrument in 2015. The PDRs, we've now had 3 of them. So 3 of the PDRs we're through, and the last one, which is MAORY, should be at the end of this year. The final design reviews will start next year, running into 21, probably 22. And then PAE, which is the factory acceptance of the instruments in Europe, should be in 24, 25. So that's the basic timescale that we're working on. Now, the reason for this very long timescale, I mean, we've already been working on some of these instruments for 10 years, is fundamentally because the amount of simulation and the amount of analysis that you have to do to make certain these instruments are actually going to work on the ELT. The ELT is just so different from anything we've done before that all of the instruments now have extremely advanced simulators so that we can really work out how they work. And we can really confirm or find out what the problems are, because we're always finding things that are not behaving exactly the way we thought they would. And so this is a table. It's slightly old, but it basically says what the ELT instrument roadmap was. So starting from about 2014, we had all the plans. There was then a series of meetings at ESO with the science community where we looked at, okay, what would be a good suite of instruments for the first light? And we were interested in scientific return and impact. Also in complementarity to the James Webb, because the James Webb should be flying maybe at the same time now that the ELT will actually have first light, but ELT will come slightly after. And also we want to be certain that we actually cover all observing conditions, because it's no good building a €1 billion observatory and then finding half the time you can't actually observe with it because you've got no instruments that can actually do any science. And so the committee's decided on the 3 instruments, which here are noted as an IFU, the ELT camera, which is the camera and multi-conjugate AO system, and then the mid-infrared system. There are 2 instruments that are outside that are going to come later, that we've already now run the phase A studies for, which are MOS and HIRES. I won't say anything about this simply because we've gone through the phase A studies and now we're in negotiations about the scientific capabilities versus the price, etc. And then there's one instrument that we desperately want to build, which is the planetary camera, PCS it's called. And so this is a super high Strel system, but with the problem that the technology currently isn't there. The technology for the DMs simply is not available at the moment, because we would need something like 10,000 or 15,000 actuators. And currently that is just not there. So we're running development programs for the technology, but at the moment this instrument is on hold until we have some idea that we can actually get to those sorts of systems. So the first of the instruments that I'll talk about is HARMONI, which the Institute is actually involved in. So it's led by University of Oxford and UK ATC. It also includes Tenerife, Madrid, and then Corral and Marseille. And so basically the project has been split down to the various different systems, and you will see for all of these instruments, they all have very, very large consortia behind them, simply because we're talking about hundreds of well, we call them full-time equivalents. So the amount of effort that you need to put in is hundreds of FTEs, which is 1 person for 1 year. And most of the instruments are coming back with about 400 or 500 FTEs, whereas for the VLT instruments, they were kind of at 200 FTEs. So again, it shows you the jump in problems that are being caused. Now, HARMONI is an IFU, an integral field unit, so it's a 3D spectrograph. It covers, well, it actually has 2 modes. One is visible, which is 0.47 to 0.95, and then the main mode, which is near infrared, is 2 to 2.5 microns. It has a series of resolving powers from 3.5 to 18,000. And as I commented earlier, it actually cuts the image up into 32,000 spaxels. And for this, we need 8 Hawaii 4RG detectors. And so it's designed to work seeing limited in the visible, but diffraction limited, using single conjugate adaptive optics or laser tomographic adaptive optics. The LTO is there simply because the SEO will give you the best Strel, but only on 0.1% of the sky. The LTAO will extend this using the lasers to about 50% of the sky at a slightly poorer star ratio. Then the spaxels, or sorry, the fields of view that we get, so even with these 8 detectors, we're only covering 6 by 9 arc seconds on the worst spaxel scale. And this one is nowhere near diffraction limited, but it's just designed to cover area. Then we have 2 intermediate scales of 20 mass and 10 mass per spaxel. So this is optimal for sensitivity for faint targets, because you can get all the light into a single spaxel. This gives you the best combination of sensitivity, and then the final mode has a spaxel scale of 4 mass, so that's 4 milliarc second per pixel. And that is diffraction limited, but we're only covering just over half an arc second. So the field of view is 0.6 by 0.8 arc second, so it's only good for very, very compact sources. And our expectation is that most people will be using the 20 or the 10 mass modes, because it kind of gives you the best combination for most objects. But if you really want true diffraction limited work, you have to go to the smaller scale. Now, the science motivation behind HARMONI, okay, exoplanets are always there, same for everybody, you'll see that on all the plots. Resolve stellar populations, because again, we can get a diffraction limit, and so you can actually start to resolve stars and external galaxies. Supernova at high redshift, QSO host galaxies, and high Z galaxies. And just to show you a change in capability, this is what would be taken on Symphony. So Symphony is on the VLT with 10 mass. And this is the sort of image that you'll get out of the ELT with 20, I think this is done with 20 mass pixels. And so you can start to see how, this is a simulation obviously, but you can start to see how much more detail and information we will gain on the ELT. So the instrument itself is huge. So it's about 7.5, 8 meters tall. It's 6 meters wide by about 5 meters. So the light comes in from this side. It goes into a re-imaging system that then brings the light down to the cryostat. And then on top of the cryostat, we have all of our natural guide star wavefront sensors. So the re-imaging system, the light comes in from the focal plane. And then it's basically just an Offner relay. But this Offner relay, we're talking about nearly 1 meter size optics just to relay the 2 arc minute field down into the cryostat. And so we have the main focal plane, which is only a few arc seconds, that goes down into the instrument. And then just above the cryostat is where we're going to mount all the sensors, all the wavefront sensors. They're physically mounted onto the cryostat, so they rotate with the cryostat. So we get minimum amount of flexure between the two. But these have a patrol area of 2 arc minutes. Then we have the LTAO system. Now, originally the LTAO system wasn't funded, but at the end of last year, Council agreed to find the funding for the LTAO, so the Laser Tomographic System. And so this basically has 6 wavefront sensors for the lasers. So the main light comes in, it reflects off a dichroic, goes up into a fold mirror, and then each of these sensors picks up one of the laser guide stars. And then this information has to be combined together to find the wavefront error that we have at that moment. And then the cryostat is again huge. We're talking about 3.5 meters across by about 3 meters tall. And inside the cryostat, we have the pre-optics, which have been designed here. It then goes into the image splitting system, into the IFU, into the image splitter here, which cuts the light up into basically 4 spectra. And then they go into the spectrographs, which are here. And like I said, because these instruments are so big, you can't now just go simply turn up with a screwdriver and expect to reach the stuff. Most of this stuff is going to be buried so deep inside that we need specific tools just to access the components. And so maintenance and such like of these instruments, simply because they're so big and weigh so much, is again a huge problem. I mean, the whole of HARMONI is going to weigh 40 tons. And then so the field splitter, the way the field splitter works is that there is a a splitter that splits it into 8 spectra, or into 8 sections. Each of those goes into an image splitter that then produces a spectra. These go into the spectrograph and then onto the detectors. The next instrument is the mid-infrared instrument, which is called METIS, and this we've just gone through the PDR. The preliminary design review was beginning of this month, so now they're making all the corrections that were requested. It's led by Bernard Brandl from the University of Leiden, and again, this is a large consortia, including NOVA, which are Dutch. A-STAR is an Austrian consortia led by the University of Vienna. And then we've got Zäckle, Zurich, Leuven, Heidelberg, and then the UK ATC. And it's aimed at the thermal infrared. So it goes between 3.5 and at least 15 microns, and there's a discussion there whether we'll do the Q band or not. It's not 100% certain that we will go into the Q band, which is 18 microns. But in this range we have images with fields of view of around 12 arc seconds. We'll also have low resolution slit spectroscopy. But of particular importance for these people, for METIS, is the chronography. They want to do high contrast imaging. So basically they want to do exoplanets. And for that you need very, very high contrast imaging and chronography. And in their instruments they actually have 3 different types of chronograph that are optimized for different things. They also have a high resolution around R of 100,000 IFU spectroscopy in the L and M bands. And this will work at the diffraction limit using, it's actually an infrared SCAO sensor. So it'll just use a pyramid sensor for doing single conjugate adaptive optics, but it will work in the infrared rather than the visible because a lot of their sources will be very bright in the infrared and not so bright in the visible. The science cases, okay, you'll see actually most of the science cases are very, very similar, but these are really going for the exoplanets. Dust-shrouded stars and such like, and rings, circumstellar nucleus, and AGN structures. I mean, that's the main thing. So you'll have the slide so you can go through this in detail. I won't go through it in detail here, but you can see that there are very interesting science cases for all of the science cases. The instrument itself, again, it's a big instrument. So what we have is the Cryostat, basically on top of a hexapod system. Here's the floor of the Nasmyth platform. Here's the beam of the telescope, 6 meters above it. And yeah, so here we have the Cryostat with all its various modules inside. And then we need a service platform so you can actually get up to the correct height. And this is just a quick schematic or simple schematic of METIS so you can see how complex it is. This is actually one of the most complex infrared or cryogenic infrared instruments I've seen. Because all of this part here is cryogenic. So it will run at basically at 10 to 20K, most of this. And so, okay, we've got a warm calibration system, that's fine. We then go into the window. There is then a pre-optic, which has the derotation, the field derotation, because it's on the Nasmyth platform and fixed. We can't move the whole instrument, so there is an optical derotator. It's inside the Cryostat, it's cold. There's also a re-imaging system to produce a first pupil, so they can block out most of the light they don't want. There's then a dichroic that splits the light off into the wavefront sensor. The rest of the light goes through a chopping system, so there's a chopper here. The ELT is so big that we can't chop. The mirrors are just too big for us to actually do chopping like they do on GTC. So here they're having to put the chopper inside. And then after all that lot, it actually goes into the system or into the various instruments. So we have the LM spectrometer, which is here. Or we have the, so this is the LM imager. And then this is the N-band imager, N and Q band imager. It also does low resolution spectroscopy. on M4. So it's part of the telescope. So we sense it here, and then it has to be linked up. And so to do that, basically, all the instruments have to send a 5,000 number vector, which gives you the wavefront error at 500 hertz up to M4. Every instrument, yes. So the next instrument is, well, it's not actually an instrument, it's the multi-conjugate AO system. The aim of this is to give a far larger isoplanatic area. So instead of being about 15 arc seconds, which is what you'll get off an SEAO system that you can actually use, this should give us a very flat PSF over nearly an arc minute. Actually, the spec is 2 arc minutes, but we have to see about that. It's led by INAF, and so most of the people involved in this are INAF, which are the Italians. Also, there's a contribution from INSU, where it's IPAG, who are French. So an idea of what it looks like. So this is the camera, which is MICADO sitting next to MAORY, and this is the MAORY system. And so it will use 6 lasers and 3 natural guide stars. The natural guide stars are actually mounted, the natural guide star wavefront sensors are actually mounted again on top of MICADO, on top of the instrument, physically moving with the instrument to get rid of differential flexure between here and here, because this is a very large distance. So any slight movement between the two and you will destroy your straw. Remember, we have to hold the images accurate to 40 microns in the focal plane. Now, the initial proposal is we'll have a single DM, but we want, so as well as the deformable mirror on the telescope, they will have an additional deformable mirror, at least one more, and probably 2 more deformable mirrors in the system. And then basically by combining these 3 mirrors, it allows you to go to a far larger diffraction limited field of view. The science field is at least 1 arc minute in diameter for MICADO, and we can actually support up to just over 2 arc minutes. And so MICADO is shown here. There is the capability of putting in a pick-off mirror and taking the beam out in a different direction, and then mounting a second instrument onto MICADO. And the aim is to get to something like a 50% sky coverage with a goal of a Strel ratio of about 50% in the best conditions. What you have to remember with these big telescopes, even if you get to a poor Strel ratio like 10 or 15%, you're so much better than seeing limited that you will still be far, far faster. I mean, obviously the better the Strel, the better, but we'll still beat everybody, even at low Strel ratios. So although we've got goals of 50%, even at low Strel ratios, we will still be very, very powerful and do a lot of very good science. And then the other thing is we need a PSF stability. So this is stability of your source has to be better than 10% across the field of view. Because if the PFS isn't stable, that again will cause blurring, which is not good. And so just a quick picture of what it looks like. So the beam basically comes in from the telescope, which I believe is over here. I think it's actually an old picture and they keep on changing it slightly. But basically there is a re-imaging system, so there's a camera collimator system. Then you have the 2 DMs, 1 DM here and 1 DM here. And then we have a dichroic. These dichroics again are big. So the dichroic on HARMONI was about 60 centimeters, which are getting to the biggest dichroics we can actually get. That's to spit out the laser light from the science beam. And again, these need a dichroic that's about 60 centimeters across. In this case, the laser light is transmitted through, and the infrared light is reflected. This then goes down to their laser guide stars. There's actually quite a strong collaboration now between the MAORY people and the HARMONI people on the development of the laser guide star system. And so the thing that goes with that is MICADO, which is an infrared imager, led by the Max Planck, but again with an awful lot of, basically most of Europe you'll find in one or other of these consortia. And certainly virtually everybody working on AO is part of one of these consortia in Europe, or nearly everybody, simply because this is a very challenging problem. So the MICADO is a near-infrared imager. It goes from 0.8 to 2.5 microns with pixel scales of 4 mass, which would give a field of view of 53 arc seconds, and 1.5 mass, which gives you a field of view of 20 arc seconds. One of the big pushes is for astrometric imaging. So they want to do high precision relative astrometry on the images that they take. And they're pushing to get down to 50 micro arc seconds. And certainly in their PDR, which was last year, one of the very large discussions was how you get down to these sorts of numbers and can actually build an instrument that is stable over reasonable periods of times. Obviously, it's based on a lot of calibration and calibration based on the sources in the image, but they want to measure things like the galactic center and such like. They also have a second mode, which is a long slit. It's a 3 to 4 arc second length slit with about 20 milliarc seconds wide. And that will give spectral resolutions, well, it's a fixed format, and so you get multiple orders across a detector, and it should get to resolutions of, it's over 10,000. I honestly can't remember the final number. But you can either do 0.8 to 1.4 or 1.5 to 2.4 microns at a resolution of about 18,000 up to. And again, they're also interested in high contrast imaging using SAO, so they've got chronograph. And to make this lot work, they actually need 9 4K detectors just to cover the focal plane. Now, their science cases, again, they have a list of all the interesting stuff in science, but this is just a simulation of what would happen if you took something like the Whirlpool galaxy on MICADO and MAORY, and you put it out to a redshift of 2.3. So now the whole size of the galaxy is just over an arc second. And so what these people have been doing, I mean, all the instruments have been doing is running an awful lot of simulations to really try and understand what they will see, including everything they expect from the instrument and everything they expect from the sky and everything they expect from the objects themselves. And so this shows you the sort of images that we should be able to take with MICADO, or MICADO and MAORY, that we can actually now do very detailed works on the structures of, like I say, it's galaxies, but now at a redshift of 2 point something. So what does the instrument look like? So again, the light comes in through the top. When it's with MAORY, there'll just be a mirror, and then the light goes down. This is where all their sensors are. Again, the sensors are physically attached to the cryostat, so everything rotates, but everything rotates together. So that's the way that we get rid of the differential flexure between the guide probes, which are driving all of our AO system, and the science instrument. And then in the science instrument itself, we have a series of apertures. There's a re-imaging system, the filters, and then it's re-imaged onto the detector array, which is down here. And then underneath it, we have all the electronics, and the whole lot rotates together. This whole thing is, again, this is 6 meters high. It's about 3 meters in diameter, to give an idea of how big it is. And then this is just a picture of what it looks like. So we have the light coming in. So these are the focal plane mechanisms. There's then a collimator here with 3 big mirrors. It comes through to where the cold stops and the filters are. There is then optics that you can put in that allows you to go to the spectroscopic mode or the high resolution mode, and then it comes down back into the camera and onto the detector. The detector is over here. And again, you're talking about 3 meters, so you can see how big the detector units are, and therefore how big these optics have to be. And that's just to cover a reasonable field of view. So in summary, I'm getting to the end now, so in summary, I just thought I'd throw up a few pictures of what we thought the instrumentation would be. So this is what we thought the instruments would look like in 2008. The whole of the Nasmyth platform, by the way, is 27 meters by 15 meters, so it's not a small Nasmyth platform. You can actually mount the whole of the VLT on one of these Nasmyth platforms. So this is what we thought it would be. With nice small instruments that just basically fitted behind an AO system. This is what it was looking like in 2012 after after the first phase A reviews design, but you can still see there's a lot of space on here. There's plenty of room to walk around. And so let's see if we can get this to actually work. And then this is what it actually looks like today. This is a full CAD model. So we have METIS here. We have the PFS, which is actually the guide system for the whole telescope, is in front. This always runs. This is MAORY here with its free imaging optics. This is MICADO. I mean, we have to build these things simply because, as you can see, maintenance is going to be a big challenge on these sorts of things. And so if we don't build the full model and put everything together, you can't see how do you actually access stuff. So this is the mirror that comes out and brings the light down into MICADO. And then HARMONI is here. This is a person to give you an idea of the size. So this is the relay optics, and then the Cryostat is underneath. Oh, I forgot to say, all the relay optics, in order to control the thermal backgrounds on HARMONI, are going to be chilled. So most of HARMONI will be run at about -30 for the optics that they can, and then the Cryostat itself is obviously run at -200. And then here we come around to the PFS. Here you can see there's a pick-off mirror, which is here, that allows you to bring the light into HARMONI or METIS, or it's removed and the light goes straight through. And this also has the wavefront sensors to control the telescope. And then finally underneath we have what is called the PDS, the phasing and diagnostic system. And these are sensors designed to phase the telescope. Also, all the commissioning stuff for the telescope will be put under here. Okay. So that's where we are with the instruments. And then just a final summary, a quick summary on where we are with the ELT. So we got the green light for construction in 2014, and now all major contracts are in place. So it's been a huge effort to get these major contracts in place. The biggest one is obviously for the dome and main structure. So this is the main structure. This is kind of halfway through PDR. So we had the first review. There was some problems, but we're now basically running into the second part of the PDR review of the main structure. The dome itself has been fully reviewed, and they're actually on the point of starting. And here are just some of the, if you look at the ESO webpage, you'll see lots of notices about all the contracts have been done. And one of them was, for example, the PFS, the phasing and the prefocal station. That's with IDOME in Bilbao. The optics themselves, again, they're all now contracted. So we have contracts for all the main optical system. This was the first blank that was made by Schott for one of the M1 blanks. The mirror supports. The mirrors themselves, the M1 mirrors, are going to be polished by Riosk, and then actually basically refitting a whole factory, which is in a different place from where they polish the GTC mirrors, for example, just so they can handle this huge number of segments, because there's 700 segments in the telescope, plus one spare of each type. So they've got over 1,000 segments to polish. And they have to produce them in a few years. So it turns out they have to, in the end, produce one segment per day at specification. M2 and M3 are in production. Blanks are coming from Schott, and again, it's being polished by Riosk, and the cell is by Sener. The M4 deformable mirror, where we've actually got the first thin shell. These thin shells are 1 millimeter thin. So it's a piece of glass that's 1 millimeter thick, or just over a millimeter, sorry, 2 millimeters thick, and about basically a meter across. And because it's so big, we couldn't do it in a single piece. We have to have 6 sectors. And so the first of those, which you can see here, has been polished and delivered to Adoptica to put the first system together. And then below that, we have a system it's actually silicon carbide, to actually support everything and to act as a support. Oh, that's right. And then the final mirror, which actually was the most difficult to do or to find a contract for, was the M5. But now we have a contract for the M5. It's simply because it's a 2.5 meter mirror that has to move at high speed. And there were very few people in Europe or even in the States who could actually take this on. And so this last picture here basically shows the site. So for those who know Paranal, this is the telescopes, the Paranal telescopes here. This is the Residencia, or the hotel. and then the ELT itself is about 20 kilometers away. And so basically, they can all use the same facility. We all have the same electrical supply, which is now coming from the national grid. And then this is where we've got to with the sites. There have been some problems actually because some of the geology wasn't quite right, so they've had to reinforce some of the pillars and such like. But this gives you an idea. Here's a lorry, just to give you an idea how big this really is. This is a lorry in here. It was taken last year, actually. So, like I say, they are progressing. We can see, the first thing to do was to put the road in so we could actually bring the stuff up. And now then they blew off the top of the mountain, and now they're digging down for all the structures. So basically, the telescope pillar is here. The dome sits out here. And here is where we have things like the integration lab and such like. I mean, we have a large integration lab, although it's not going to be large enough, just to reintegrate the instruments when they get to Paranal. But yes, so now work is actually ongoing, and you start to get the feeling that we have a real project. But as all these big projects, we will run into delays. Anyway, thank you very much.
Okay. Yeah, thank you very much. So we are now to questions, and we have.
Peter, I think you made an interesting point at the beginning when you were comparing the capabilities of ELTs and centimeter class telescope in limited condition. If we buy the full argument, would that mean that building an instrument for operating at sin limited condition, the DLT doesn't worth the time?
It is worth the time as long as you stay on a restricted field. So if you just got a single object, or an object that fits within the field of view of your instrument, then it will be 20 times faster or so than the VLT. So it means that 1 hour on the ELT would be the equivalent of 2.5 nights on the VLT to do the same thing. So you do win. The problem comes is if you want to cover a large area, and so you have to do multiple images.
So for that science cases,
and so
class telescope are possibly.
For those science cases, you have to be careful that you don't. If you wanted to cover a square degree of sky, for example, the ELT would be a really bad telescope for that.
Okay, any further questions? All happy with knowing already enough about the ELT? Okay, then I thank very much the speaker for this highly interesting talk. Thank you.
Thank you.